In 2016, researchers at OpenAI trained a neural network to play a boat racing game called Coast Runners. The objective looked pretty simple. If you race around the track, finish ahead of your opponents, you win the game. But the AI didn't try to win the race. It discovered that hidden in a quiet corner of the map, you can collect the same handful of respawning power-ups indefinitely. And the points from that, even while the boat was on fire, even while finishing dead last, added up to a higher score than actually winning the race. By every measure that actually mattered to the AI, it had succeeded brilliantly. It found the highest scoring strategy any Coast Runners agent had ever found, but by every measure that mattered to humans, it had completely failed. This is a video about why AI systems cheat, and as we're going to see, it isn't really a story about AI. It's a story about the gap between what we want and what we say. To understand what just happened, we need to talk about how these systems actually learn. In reinforcement learning, an agent takes actions in some environment. The environment sends back two things: what the agent sees after its last action and a number. The number is called the reward, and the agent has exactly one job: pick actions that over time make the sum of those numbers as large as possible. That's it. It's pretty simple. Now you have to understand there is no line of code that says win the boat race. When you're training these agents, there is only the number or the reward, and the agent makes the reward go up. That's all it does. So when the OpenAI team sat down to train their boat, they had to translate win the race into a number that the agent can see. And the way they did it, and the way almost everyone does it, was to hand out small rewards along the way. Points for hitting checkpoints, points for collecting power-ups, and points for finishing. You can see what they were trying to do. They were trying to leave a trail of breadcrumbs and tell the boat, hey, if you go this way, you will cross the finish line. But the AI doesn't see breadcrumbs. The AI just sees numbers. And it turned out that if you could find a place where the power-ups respond quickly enough, you'll end up getting a higher reward even faster than you would if you just finished the race. This has a name. We call it reward hacking, or sometimes specification gaming. It's when the agent does exactly what we asked, it just isn't what we wanted. And once you start looking, you see this problem everywhere. My favorite example comes from a team that was training a simulated creature to run fast. They rewarded the creature whenever it moved forward quickly. It would convert its height into forward motion, which was technically faster than walking, but clearly not what anyone meant by running. In another example, we have a robot arm that was being trained to hold a ball. Its reward function was being given by a camera. Instead, it just learned to position its hand between the camera and the ball, such that when the camera looks at it from its perspective, it looks like it was holding the ball. And of course, I can't make this video without mentioning large language models. In the early days of large language models, they were heavily optimized to produce responses that humans rated highly. And through that, we rediscovered something that humans have known about each other for a long time: that the easiest way to get a good rating is to tell people what they want to hear. We call this sycophancy. In a very real sense, it's the chatbot version of the boat going in circles to collect the power-ups. And what's really interesting is that in every one of these cases, the system is doing exactly what it was told. The problem is that what we told it to do versus what we wanted turned out to be different things. Now let's give this gap a name. Imagine that what we truly want, let's call it R star. Maybe it's be a good racing agent, maybe it's be a helpful assistant. This is the function in our heads. Now imagine that the thing we actually managed to write down, call it R, maybe it's points for a power-up, maybe it's a thumbs up from human raters, or maybe it's a camera that says it sees a ball. Near the middle of this graph, for ordinary, sensible strategies, these two functions track each other pretty well. A boat that's good at racing does collect power-ups. An assistant that's helpful does get good ratings. A creature that runs does move forward quickly. But out at the edges, for weird, extreme alien strategies, the two curves begin to come apart. And if there's one thing that sticks from this video, it should be this. An optimizer doesn't climb the function we wanted, it climbs the function we wrote. And if the two functions are nearly identical everywhere, fine, no problem. But every real-world reward function has corners and edges where it diverges from what we meant. And a sufficiently determined optimizer will find those corners, because that's the definition of what an optimizer is. It's going to explore every possibility and find the one that maximizes. And by the way, humans are very guilty of this as well. There's an old idea from economics that says this pretty beautifully. It's called Goodhart's law. When a measure becomes a target, it ceases to be a good measure. Teachers know this. If you only reward the test scores might go up, but learning does not. Maybe students cram, maybe they cheat. Managers know this. If they pay for lines of code, programmers write longer code, not necessarily get more work done. Anyone who's ever set a metric for anything has sooner or later watched a metric and goal walk away from each other. One of my favorite examples comes from 1902. In 1902, Vietnam was just being overtaken by rats. And so, the French, colonizing at the time, paid a bounty per rat tail to control the rat population. The people, trying to maximize their reward, which is the money, started catching rats, cutting off the tails, and releasing them. And the reason for that was because a tailless rat could go on to make more tailed rats, which meant they could get more reward. Some entrepreneurs even just started farming rats, and the city ended up with more rats than before. There are plenty of fun examples like this, but I want to slow down because there's a subtlety that makes this all a lot more interesting for AI than for humans. When an agent isn't very capable, it can't reach the weird corners. A bad boat racing AI will just crash into the wall. A bad language model just produces gibberish. Their behavior stays in the middle of the graph where R and R star happen to agree and everything looks fine. But as the agent gets more capable, as it explores more, optimizes harder, finds clever strategies, it climbs higher on R. And the higher it climbs, the more it tends to drift towards those edges. The corners, the places where the function we wrote and the function we meant come apart. This means something a little uncomfortable. It means that a system that seems perfectly aligned at low capability can become misaligned simply by getting better at its job. Nothing about its goals change, nothing about the rewards change. The only thing that changed is that it got good enough to find the gap. The boat racing AI was a charming, harmless example because the stakes were a video game score. But the same dynamic, a small gap between proxy and goal, optimizer finds the gap widens with capability, and it does not care what the stakes are. So now we can ask the question this whole video has been building towards. What happens if the agent is not playing a boat game, but operating in the real world? What happens if the reward isn't points on the screen, but something like human approval or engagement metrics or the number on a quarterly report? What happens if the optimizer is not a small neural net trained for an afternoon, but a system orders of magnitudes more capable deployed across millions of decisions? We don't have a clean answer, and that's kind of why this is an open problem, but we can sketch the worry. The worry is that every reward signal we know how to write down is a proxy. Human ratings are a proxy for human preferences, and human preferences are a proxy for human flourishing. Every metric we can measure is a measurable shadow of something we actually care about. And the shadow and the thing are not the same. For systems that are weak, this doesn't matter very much. The shadow is good enough. But for systems that are strong, the shadow might not be enough. A sufficiently capable optimizer pointed at the shadow will, given enough room, find a configuration of the world that maximizes the shadow while leaving the underlying value behind. Kind of like the boat in the lagoon, on fire, but winning. This is one of the many subcategories of the alignment problem which we're going to continue to explore on this channel. It's not that the AI turns evil, it's not that the AI rebels, it's just, hey, we asked for the wrong thing very precisely, and it gave us exactly what we asked for. I want to leave you with one thought. When we look at a boat that won't finish the race, or a robot that flips itself over instead of walking, or a chatbot that flatters us instead of telling us the truth, the natural reaction is to laugh. These look like failures, and they look stupid. But they aren't stupid. There's something much stranger, and I think more interesting. They're systems doing exactly what we told them to do with a clarity, patience, and thoroughness that we ourselves did not have when we told them. The cheating, in other words, is more of a mirror. It's the optimizer holding up our specification and showing us very precisely what we actually wrote down as opposed to what we thought we wrote. I hope you enjoyed that and I hope you learned something. This is Good Robots, a channel about how we actually get AI right. I'm working through the biggest problems in AI safety one at a time, so please subscribe if you want to follow along.